blank note cards up there. So if you want to grab one on your way out, that's fine, so that you can start like making your list of things for chapter 5 that you want to make sure that you put on your note card. So you may want to do like examples of chemical reactions for identification. At the end, in a couple of slides, we'll go through some examples of what types of questions you'll see. So we were talking about hydrogenation. So hydrogenation is hydrogenation. So it's just adding hydrogen to a double bond. So this happens when you have alkenes. This happens when you have carbons with double bonds between them. To convert them to single bonds, a simple way of doing this is just adding hydrogen. So this is what a hydrogenation reaction is. Typically, there's some kind of catalyst, like platinum in this example. So interesting thing about hydrogenation is this became a very common practice in production of food materials. So when you had fats typically are animal source. So you're talking about butter. Butter comes from cream that's been churned. The problem is if you don't keep it cold, it goes rancid. So butter, it'll start getting kind of almost like a sour or sort of a smell to it. And if you had a chance this week and you were at the grocery store and checked some of the expiration dates on butter and compared it to margarine, you would notice that there's months in terms of difference. So butter is usually a 6 to 8 week time span that it is okay. And then it starts kind of getting darker and darker yellow. And then you might start to notice that odor, as that tells you that it's pretty much done and time to toss. Whereas if they take an oil, like corn oil, vegetable oil, olive oil, if they take oil, which has that unsaturated fatty acid, which is just the long carbon chain, has at least one double bond in it, and they hydrogenate it, they can convert that double bond into a single bond. And so that allows those molecules to pack in really tightly, and that'll allow that oil then to become solid. We don't really want it solid like butter, because you know how like butter is really hard when you take it out of the refrigerator. But margarine, they found if they partially hydrogenate it, which means that they convert some of the unsaturated fatty acids into single bond solid saturated fatty acids, you kind of get this mix. So you get like a soft butter. And so that's easier to spread, easier to cut. It can add artificial butter flavoring. Hence you end up with the things like, I can't believe it's not butter. That just has artificial butter flavoring in it. So it tastes like butter, but it's actually made from partially hydrogenated oils. The plus of this, one, it's softer, easier to spread, but two, the shelf life is 3 to 4 times longer than the shelf life that you have for butter. So this was developed in the 1950s and then was really marketed very well. That's one of the big things. So it's all about the marketing. So it was pushed as being great because of this shelf life. You don't even have to refrigerate Crisco. And so you can use that in your cooking, and it's got the same sort of texture that butter would have without having the refrigeration and without having the worry that it's going to go rancid or go bad. But in the processing, if they partially hydrogenate, the steps that they were doing was converting some of the cis double bonds were converted to saturated single bonds. But there was a small percentage of those cis double bonds that would be converted to a trans double bond. So really like the double bond would start to open, but it would close back again. And so instead of going completely to the single bond, when it would close back up, it would close and create the trans double bond. The challenge with that is that there is no known enzyme in your body that has the ability to break down a trans double bond. So remember cis and trans. Cis is when the molecules off the double bond, both of the groups point up or point down. So I always say cis looks like they're sticking off the same side. So in that example here, you can kind of see how it looks like they're both sticking upward, projecting up, kind of creates almost like a permanent U shape or a hump in the molecule. Whereas trans, one of the groups sticks up, the double bond doesn't rotate, the other group sticks down. And so they're stuck that way. There is no known enzyme that can digest or break that structure. And so there comes the question. In the 80s, they started saying, well, if we can't digest this, what happens to it? So it gets absorbed. It gets absorbed into the bloodstream. But what happens to these trans double bonds? They found that high levels of trans fats in your diet increases your risk of coronary artery disease. So coronary artery disease is when you have fats and cholesterol circulating in your blood. They may begin to stick to the walls of the vessels. And so I just think about plumbing, like in your pipes, commonly, you get this like sludge stuff that begins to build up on the pipes. That's kind of normal over time. As long as you're running hot water and soap, it usually kind of like breaks it down and keeps it moving along. Same thing happens in your blood vessels. If you have fatty material, does it mix with water? Does fat mix with water? Oil mix with water? No. And so fats and oils are not going to mix and stay mixed in your blood, which is watery. So instead, it may get released and stick to the blood vessel wall. So if you look at this picture over on this side, this is like a normal tube, a normal blood vessel. And so blood would pass through basically on its way in circulation. But if you look at the little picture to the right, notice how you start to have this narrowing of the vessel because of fat that builds up. And so you can definitely see that this would be more difficult to pass fluid through this narrow tube because of restrictions from fat, cholesterol, plaque is what they typically call it, that plaque buildup. So they did find that trans fats seem to increase the amount of circulating fat in the blood, increasing the amount of plaque that builds up on those vessel walls. And finally, in 2013, which was about 8 years after Europe banned trans fats, the FDA in the United States finally said, okay, well, there's enough evidence that maybe we shouldn't have this in food. Then food manufacturers said, wait, you can't do this. Like all of your foods that are in here shows sort of like the cis. Those are the naturally occurring cis bonds. When you partially hydrogenate, sometimes the double bond, instead of converting to a saturated single bond, you will end up converting that cis double bond into a trans double bond. So that bottom picture shows a trans fat. So the name of it just really refers to the shape of that double bond that occurs. When they said, where is it? Here it is. When they said, so we are going to outlaw trans fats, food manufacturers had a huge issue because here are some of the most common, where's my zoom? Some of the most common, let's see if I can make it stop, foods. How many of you have eaten any of this week? Show of hands? Yeah. Okay. So you're looking at all of these like prepared, prepackaged, already sort of, I think of them as like convenience food types of foods, popcorn, frozen pizza, the little biscuits in a can. You have the margarine, cookies, cakes, things that are pre-done, pre-made. I'm trying to get the gray to go. There it goes. Okay. Frostings. So food manufacturers had taken partially hydrogenated fats and cut out the butter, used the Crisco and the partially hydrogenated fats because they can make these foods and they don't go bad for a much longer period of time. So the cookies will stay soft. They don't get all dried out like what happens quicker when you use butter. And so the food manufacturers really threw fits. They said like, well, you can't outlaw this because we won't be able to make all of these foods again. And so the FDA relented and said, okay, you can have 5 years. You can have 5 years to retool your recipes so that you take any partially hydrogenated fats containing trans fats out of your recipe. So even though they outlawed it in 2018, it didn't actually go into effect in 2013. It didn't actually go into effect until 2018. And even then, they got an extension. So it was actually May of 2019. May of 2019 was truly when the ban on trans fats being used in any type of prepared food came into law. But at this time, we were almost 20 years that Europe had stopped doing this. So there was a lot of questions. And so you'll still see partially hydrogenated fats. All that the food or the margarine Crisco producers had to do is they had to do an extra step. They had to do a step to make sure there were no trans fats produced. So if there's any unsaturated, any double bonds, they remain in a cis conformation. So it was a couple extra steps in order to be able to do that. So you will still see food that has partially hydrogenated oil, margarine, as its primary fat source. And that's fine, but now it won't have any trans fats. That is a requirement. But you still see foods with packaging that say no trans fats. And I'm like, well, trans fats have actually been illegal now for a couple of years. But it really was all these convenience foods that you saw them in. So there is some benefits to them, that the flavor, packaging, shelf life, but then those risks that were shown ended up sort of outweighing the difference between the benefits. Last one, okay? So remember, hydrogenation is adding hydrogen to a double bond. Hydration, when you think of hydrating, what do? Drink water, right? So a hydration reaction is adding water to a double bond. So hydrogenation is adding hydrogen to a double bond. Hydration is adding water to a double bond. And so you can see in this, remember that carbon always has 4 covalent bonds no matter what. It's got to have 4. So in the first example, because there's a double bond, you just have 2 single bonds on each carbon side, making there 4. So that double bond, remember I told you last time, the double bond is more reactive than a single bond. So that is sort of the weak spot in the molecule. So if you add water, and again, you typically have to use some kind of catalyst. This is in an acidic condition. This will speed up the reaction and allow the water molecule, which just think of water then as H and OH. So we have a hydrogen and an alcohol. It's going to add a hydrogen and an alcohol to the carbons that have the double bond. Just like in hydrogenation, you just add a hydrogen to the carbons that have the double bond, and that converts it to a single. Same thing here. It's an addition reaction because you're adding it to that double bond, creating the single bond. And it's more stable as that single bond form. So notice you end up making an alcohol group. So in this one, this just shows you sort of the general form. So there was a Russian chemist that studied hydration reactions. This was like his life's work. And in fact, the rule, kind of like with Avogadro's number, Markovnikov, studied addition reactions. So he took lots of these double bonded carbon molecules called alkenes, and he did these reactions where he added water to the double bond and then detected what the products were. So he was really asking himself, like, does that alcohol group randomly add to one of the carbons or the other, or does it always get added to a specific carbon? And he found there's actually was a rule. So the rule is when you do a hydration reaction, you would always add the hydrogen to the carbon of the double bond that has the most hydrogens directly connected to it. So notice in this example, this one actually shows you a molecule. There's a propane with a double bond, makes it a propene. So you notice it's just a 3-carbon molecule. But if you look at the carbons on the double bond, do you notice that this left carbon has 1 hydrogen? The right carbon has 2. And these are hydrogens directly connected to them. So he found whenever he did this, that the hydrogen always ended up on the one with 2 hydrogens. So he found that he would always end up with the hydrogen on the carbon of the double bond that already has the most hydrogens. And that means the alcohol group ends up getting added to the other one. If they had the same number of carbons, so if they both had 1 carbon or they both had 2 carbons, then it didn't matter. Then it really was random. Half the time the alcohol would go on one, half the time the alcohol would go on the other. But if the Carbons had different numbers of hydrogens directly connected to them. The hydrogen always ended up getting added to the side that already has the hydrogens. That's going to break the double bond into a single bond. So notice you still have the 3 carbons, but notice on the product side, that right carbon now has 3 hydrogens, and it's the middle carbon that now has the alcohol group. So on your test, I'm not going to ask you to finish chemical reactions, so I'm not going to be like, complete the reaction of this. I just want you to be able to identify them, okay? So really kind of looking at the patterns of what happens in reactions is really the sort of goal that you're going for. So in this first one, what kind of chemical reaction is that? Mg plus Cl2 makes MgCl2. Is that a synthesis, decomposition, single displacement, double displacement? It is I think I heard it. It's a synthesis. Yeah, you just have to say it loud enough I can hear it through your mask. Right? So that is where we have 2 reactants, 1 product. That's a synthesis. What about CuO plus H2 makes Cu and H2O? It's an exchange. Which one? Is it a single or a double? It's a single because we have an element and a compound. So this is a single displacement. And you can remember that if you have a compound and an element swapping a single pair, that's a single displacement. Or single replacement. Means the same thing. Some people call it replacement. Some people call it displacement. It's really just a single swapping that occurs. Okay? Now what about this? So if I have a carbon, if I have an organic molecule with a double bond and I add water to it, what is that reaction? Nope. Combustion would be plus oxygen making CO2 and water. When I have a double bond, notice that you're breaking the double bond. It is a hydration. Yep, we just talked about it. So this is a hydration reaction. But what about the bottom one? So the bottom one, I have a double bond and it becomes single bonds. But I'm not adding water, I'm adding hydrogen. What is this? No, not hydrolysis. That's breaking things into 2 pieces. Hydrogenation, okay? This is adding hydrogen. So remember the name. So if you see it, double bond and hydrogen gets added to it, hydrogenation. So if you can remember it as hydrogenation. Okay, so you see the difference between the 2 of those. So they're similar in that they're both converting double bond to single bond, but hydration is adding water to the double bond. Hydrogenation is adding hydrogen to the double bond. All right, so now in these ones up at the very top, I may ask you to identify what reactants are oxidized, what reactants are reduced in these reactions. So CuO plus Fe makes Fe2O3 and Cu. Oh, we're not going to do this one. I knew there was one I was going to fix. What happens to CuO? So the trick, remember, with oxidation reduction is look at the reactant and then find the most similar product. What is the product that's the most similar to CuO? Just Cu. So tell me what happens to it. What happens to Cu? It loses its oxygen. So everybody see that? So I went from CuO to Cu. This is a single displacement reaction. So if I lose oxygen, what is that? Oxidation or reduction? That's reduction. So you would say that CuO is reduced. You always identify the reactant as being oxidized or reduced. So what happens to Fe? Yeah, so Fe goes to Fe2O3. So do you see that the product that looks the most like the reactant, it has gained oxygen? And if it gains oxygen, that is oxidation. So you would say that the Fe is oxidized, or you could say that it undergoes oxidation. Oxidation is a noun. Oxidize is kind of a verb. They're saying the same thing. All right. What about Al plus Br2 makes AlBr3? It is a synthesis, right? But in terms of oxidation reduction, which one of these gets oxidized? Why? So what do you have to recognize with this one? It doesn't increase or decrease in oxygen. There's no oxygen. There's no hydrogen in the reaction. I heard it. It's a transfer of electrons. Aluminum is a metal. And what do metals always do when they form an ionic bond? Metals always goes from Al to Al plus 3. So does it gain or lose electrons? Lose. Metals always lose electrons. Go back. So it loses electrons. So what is that? Loss of electrons is, I always remember LEO. Loss of electrons is oxidation, LEO, so Leo. Bromine is it's not a metal, it's a non-metal. Right? And the charge on the bromine always ends up being -1. So does it gain or lose electrons? It has to gain. In order to become a negatively charged ion, it must gain electrons. And if you gain electrons, gain of electrons is reduction. So this is reduced. So I learned this in school as Leo and Gur. Leo the lion goes Gur. LEO, loss of electrons is always oxidation. Gain of electrons is always reduction. All right, so I kind of changed these bottom ones because I don't want you to complete the reaction because I'm not going to ask you to do that on an exam. But you tell me, what kind of reaction is this? CH3CH2O, C with the double bond O, CH3 plus H2O makes CH3CHOH. And OHO, C with the double bond O, CH3. What happens in this? Look at the reactants. What happens in this reaction? What does the water do in this reaction? It's not oxidation or reduction. It's not oxidation or reduction. So what does condensation do? Does condensation use water or form water? Right, so it's not condensation, what's the opposite of condensation? Hydrolysis. So this is a hydrolysis reaction. Using water to break. So remember I told you that oxygen is always the weakest part in a chain. So if I add water, I'm going to split it right there. It'll split it into two pieces. Add a hydrogen onto the oxygen. That's what makes the alcohol group on that right side, on the right product. Add the OH or the alcohol group from the water to the left molecule. You can see the oxygen, the alcohol group there. So that's where the water goes. So the water goes to split the molecule in two. That is hydrolysis. But in this bottom one, I'm not splitting the molecule in two. What am I doing with the water? It's getting rid of the double bond. So you see the double bond, the alkene in the reactant. It is a hydration reaction. Okay, I'm using water to break that double bond. Okay, we'll do a couple more. What's this top one? So 1, 2, 3, 4, 5, 6, 7 carbons plus hydrogen in the presence of an acid catalyst. Remember that sometimes you'll see something written above the arrow. It's always a catalyst. Remember, catalysts are not used up in the reaction, but they help to speed the reaction up by lowering the activation energy. So what does it do? The top one, the red one. What's happening? Yeah, we're adding hydrogen. So what is this reaction? This is hydrogenation. We are breaking the double bond into all single bonds. So notice now all the carbons in the middle are all CH2s. So CH2s would indicate they're all single bonds. With the double bond, you would always see the double bond. So I would always put the double bond in if it's anything other than all single. This one here, this one is actually one that we're going to talk about in the next chapter. So in that first one, that is sucrose, which is table sugar. Sucrose is glucose and fructose linked together. So I use water, and I end up with 2 single sugars. I end up with glucose and fructose, but notice now they're not connected. What kind of reaction is that? It's a hydrolysis. Yeah, good. So this is also a hydrolysis. That is where you use water to split a bigger molecule into 2 smaller pieces. Do you see where the water ends up? Do you see where the H and the OH? So here's my oxygen. And remember, I told you oxygens are always like the weakest link in a chain. So that is why that water can add the OH. Oh, there should be an O. That's because I redrew this to try and simplify. It should be right there. Sorry. So the OH and the H. There's where the water gets added in splitting the molecule into 2. Hydrolysis, using water to break a molecule into 2 pieces. Okay, here's an oxidation reduction question. HCl plus N2 makes NH3 and Cl2. So what happens? What happens to HCl? Okay, what does it become? So find HCl, then find the similar product. So if the similar product is Cl2, what happened to HCl? It lost. So if it loses hydrogen, is that oxidized or reduced? It's oxidized. Okay, now look at N2. What happens to N2? It gains. Do you see that it becomes NH3? So it's gained hydrogen. And that means that it is reduced. One gets oxidized, the other reactant's always going to be reduced. So what happens in this one? C6H12O6, so that's a sugar, plus oxygen makes C6H10O7 and water. So what is the most similar product to C6H12O6? So you see that looks the most like it. So we're kind of doing this comparison. So what happened? It lost hydrogen and yeah, it actually looks like it gained, but it's really this swapping of hydrogen. So we lose hydrogen because we went from H12 to H10. So if we lose hydrogen, what is that? It's oxidized. And then when you look at the oxygen, what happens to it? It gains that hydrogen. And remember that rule of thumb, if oxygen is a reactant, it is always what? It's always reduced. It's always the source of oxidizing something else. It'll either pick up hydrogens or it'll actually donate its oxygens to try and oxidize other molecules. So in this example, it gains hydrogen. It goes from O2 to H2O. So we have actually gained hydrogen. In that process, that's reduced. So if one reactant is oxidized, the other one's always reduced. Just look at the reaction, find the most similar reactant and compare it to the most similar product. And then ask yourself, okay, did I gain or lose electrons? Did I gain or lose oxygen? Did I gain or lose hydrogen? And identify it or categorize them that way. All right, so what is the top reaction? What kind of reaction is that? Not oxidation reduction, just in general. What kind of reaction is it? C4H10 and O2 make CO2 and water. Like in terms of the types of chemical reactions, what would you call that? No, it's not a double because it's not two compounds. What makes this one unique? It's that weird oxygen in there. But what is that? Something plus oxygen makes carbon dioxide and water. What do you call that? Nope. It is a combustion. This is a combustion reaction. Remember, this is burning. That's a fuel. Any kind of carbon source, whether it's CH4 or C2H6, you could go all the way up to C4H10, that's butane, okay? Like your Bic lighter. So that's the reaction that happens every time you flick a Bic lighter. The butane gets released, combines with oxygen. That spark is what lights it, and it'll stay lit as long as you can hold your thumb there. This is a combustion reaction. So remember last time we talked about combustion reactions. Just recognize you're always going to see this. You'll always see this part in a combustion reaction, right? It's going to be some kind of carbon source, some kind of fuel, plus oxygen making carbon dioxide and water. If you don't have enough oxygen, then you can have two potentially hazardous products. What are those? Carbon monoxide, remember that's the odorless, colorless gas that if you inhale small amounts of it over time, you can pass out, lose consciousness, and basically suffocate over time. And the other thing, remember the picture on that slide. No, you're not going to make peroxide. That's way too reactive. But instead of carbon monoxide, if there's not enough oxygen, you can also end up with this buildup that becomes a fire hazard. Just carbon, right? So remember, black carbon soot begins to build up. If that happens in your chimney, it can build up and create such a layer that it will be like charcoal briquettes lining your chimney, right? And you know that that'll burn. If it gets hot enough, it can ignite, and then you end up with a chimney fire. So those would be incomplete. The examples I would give you, if you see something plus oxygen making carbon dioxide and water, then you know that's a combustion reaction. Okay, so what's the next one? Not oxidation reduction or anything like that, just general reaction. What is that? It's not a synthesis because you see that you have two reactants, two products. Think. Two reactants and two products. NH3 plus O2 makes N2 and H2O. It's an exchange. Which kind? Is it single or double? It's a single. So this is a single displacement. Do you see that you're swapping one pair? So the hydrogen gets bumped from the nitrogen to the oxygen. So we have a compound in an element making a different compound in element in this reaction. What about the second one? What is it? It's not a synthesis. So two reactants, two products. It's a single. It's another single. Okay, do you see that you have a compound in an element making a different compound in an element? So this is also a single displacement. It's an exchange, but since you have a compound in an element, they're really just swapping. One pair gets swapped. What about the last one? It's a synthesis, right? Two reactants making one product. Last one. What happens here? CH3, so if you look, what's happening? It is not a hydration. It is not. If it was a hydration, we'd be breaking a double bond. Are you breaking a double bond? No. Okay? So notice the double bond oxygens, that didn't change. But what did I do to this bigger molecule? Did I make it bigger or smaller? I split it, right? And I split it using water. So what is that? Hydrolysis, right? So there's a lot of hydros. You have hydrogenation, hydrolysis, and hydration. So this is hydrolysis. So remember, hydrolysis, you're splitting a molecule into two pieces by adding water. And typically, you're adding it at an oxygen. You're adding it if there's an oxygen in the chain, that's where it's typically going to break because that's the weak link. So see right here. That's the spot that's the weakest spot along the chain. Okay, so look at the one that we were doing. This. First example at the top. I know. Reconnect. It's like, hold on a minute. There. This is that handout. Back page of the handout that I gave you on Tuesday. So look at this. What kind of reaction is this? Synthesis, decomposition, single displacement, double displacement, combustion, hydrolysis, condensation, hydrogenation, or hydration. That's all of them. Okay? So you may need to just like sit down and like list those and then write a description, maybe an example to help you like pick it out. What about synthesis is going to help you remember? What about decomposition is going to help you remember? Put that on your note card. So what's the first one? What's the first one? It is a hydrogenation. Yay. Hydrogenation. Using hydrogen to break a double bond. What's the next one? Synthesis. Stop that. I'll get back here. Hold on. So this is synthesis. 2 reactants, 1 product. What's the next one? Combustion. What's the next one? Single replacement. What's the next one? This is a new one. It's not hydration. That's breaking a double bond by adding water. What's this one? What's happening to that one? It's a condensation, right? So this, can you see that those 2 molecules got put together? So they got put together by removing water. So I pulled a hydrogen off of the nitrogen, the alcohol group off of that carbon side that made water and formed the link. So remember, hydrolysis is when you split a molecule using water. Condensation is when you can link 2 molecules by pulling water. Pull a hydrogen and an alcohol group off of 2 different molecules, and that'll form that link between them. So this is a condensation. Glass sweating is just it's not a condensation reaction. Glass sweating is just water vapor in the air condensing on a cold surface and creating water. Enough water that you can actually feel it, liquid water. It's like the blasted fog that builds up in my car every morning when I'm trying to drive to work. It's just from the hot air or hot steamy air in the car, I guess. That would be me. All right, what's the last one? Hydration. Good. So spend some time going back over these ones. Go back over the slides. There's actually a last PowerPoint slide that I didn't put any answers on. See if you can answer those. See if you can identify the group, what the reactions are. If there's any that you get stuck on, let me know. I will save this and I will post it as well. So you have, I gave you the little handout, but you've got that there to be able to compare. So that's really like in these reactions, this is the kind of questions that you're going to see on an exam. Okay, so asking you to identify what kind of reaction is this. So you've got to look at it and notice the sort of like they all have sort of patterns to them. to identify hydration, hydrogenation, hydrolysis, synthesis, single displacement. And I put single displacement in